welcome back. Last week we looked at gauge theories at the classical level, and we derived a Lagrangian invariant under a local gauge symmetry under the gauge group SU2. So the Lagrange density that we derived had this form here. And this was the objective. We've completed it at the classical level. The objective was to build some dynamical theory that's invariant under a local gauge symmetry. So we succeeded in that task. We found a way to build a theory that's both invariant under a local symmetry, and in fact, the symmetry group that we looked at last was SU2. The one we looked at first was U1. We managed to find a theory that's invariant under this local symmetry group, which does an independent SU2 transformation at every location in space-time. And we did that by adding in a helper field that we call A. So A is this gauge field, and that's what allowed us to write down a dynamical system which is non-trivial. So remember, it's relatively easy to write down dynamical systems that are trivial and invariant under local symmetry groups, but finding ones which are non-trivial, which give dynamics to, say, both the fermion field and the other fields, is not so trivial. But we managed to work it out with the help of this gauge field A. And then this gauge field A, we promoted to being a first-class object in our classical field theory by giving it itself dynamics through this curvature tensor there. So F is the commutator, I'll suppress that index for the moment, of these covariant derivatives. Okay, so this was all classical. And that's a very beautiful classical theory. We could spend a long time talking about this classical theory. So there's lots of stuff known. There's lots of interesting comments to make about this theory. Firstly, it's not quadratic, right? In contrast to most classical theories we start with, this one's not quadratic. And it's it leads to nonlinear equations of motions in general. And these nonlinear equations of motion have very interesting solutions at the classical level. So we won't have much to do in this course with the classical theory of gauge theories, either abelian or non-abelian, but so they really are interesting, these theories, just even at the classical level. And these interesting features at the classical level also sort of play some key role in the quantum theory as well. So there's these soliton, instanton type solutions to these things, which are like a little bump, a non-trivial bump in the gauge field A, which is there at the classical level, and they also manifest themselves at the quantum level in relatively interesting ways through interactions. But we won't be able to talk about this relatively advanced theory. All we're going to aim for in this course is the perturbative quantization of these gauge theories. I'm going to put the scare quotes around the word quantize. As I've emphasized, I guess, enough now in this course, quantization is a guess. It's an educated guess based on experience of a quantum system that's invariant under all the symmetries that you want it to be invariant under. So in particular, we want to find a quantum system that's invariant under the Poincare group. And this local gauge. And invariant under means gives you a representation of, so that's what we want to find. We want to find a quantum system invariant under the Poincare group and the local gauge group G. And if we could do that, then we would legitimately have a quantum gauge theory, right? And it's not so easy, well, and there's also this final criteria which is left unspoken, which has as its effective classical So you want three things, right? You want a quantum system, first of all. You want that it's invariant under all the right symmetries, so that you can legitimately call it gauge theory in the quantum level. And also, you can find things that satisfy these two things, right? The Hilbert space C, right, is super trivial. It's just everything's represented by the number 1. And indeed, it is invariant under the Poincare group and the local gauge group in that sense. No problemo. But it's pretty boring. And the way we select out ones that are interesting is we demand a bit more, right? We demand that their classical limit, the effective classical theory that describes its classical limit in the limit of low energies and large amounts of decoherence, we want that that effective theory is precisely this classical one here. So, you know, well, that's a lot to ask. Do we get it? Well, we sort of get it. We sort of get it in this course. There's two problems which are more specific to gauge theories than other theories. So, problem number 1. Problem number 1 is not really specific to gauge theories. But in the other examples we looked at, we didn't quite have it so bad that the classical theory was nonlinear. So to remind you all the way back to the bosonic field, the single scalar boson field, there was a classical theory that we could start quantizing, namely the Klein-Gordon theory. We could guess a quantum theory that corresponded to the Klein-Gordon theory. And then you could add in interactions as perturbations. So that was fine. And then the fermion field, we had the Dirac field, which is also quadratic and easy to quantize. And then you could add in interactions perturbatively. Here, the interactions in some examples are just strong even at the classical level. So to get started is already hard. You know, finding a quadratic system with which you can perturb around to get a feel for what the solutions look like is already hard because the interactions are kind of built into these gauge theories. So the classical theory is nonlinear. So there's no kind of, there's no L naught which is not got interactions in it that you can quantize independently, apart from the trivial case, which we won't discuss so much. And then, well, there's actually there's really a lot of symmetry in this model. So in the models we're used to so far, they've been invariant under perhaps some global group of symmetries. And this theory is invariant under a global group of symmetries, Poincare group, but it's also invariant under like essentially an independent SU2 symmetry at every point in space-time. So there's a lot of equivalent configurations that this theory has, and that manifests itself in extra divergences when you quantize. So I'll show you how that happens in a second when we approach it with, say, the path integral quantization recipe. And so this is going to lead to, the first thing is just tough, like there's no way to deal with that really. We will find some limits where we can deal with things perturbatively, but the fact of the matter is, for the gauge theories that model reality, that make up the standard model, the coupling constants are just big. And you can't use perturbation theory at this sort of low energy level anymore. However, we do get out something, a limit where we can talk about things, and that's the limit of high energy scattering. It turns out that we can use perturbation theory there. I'll say something about that in this course, but not too much, I'm afraid. So point the one, there's not much we can do about that. Point the second, yeah, that's a sort of more tackleable problem. It leads to lots of divergences, but we'll learn in this lecture how to deal with those divergences, like these spurious symmetries that we get here. So we have two problems, and I'm going to tell you about two approaches and their pros and cons. So approach one is this. Just super naively path integral quantize. That's what we're going to do today. And I'll explain later how these two problems manifest themselves in the solution of this path integral. So this allows us to guess quantum theories, this path integral quantization recipe here, which are locally gauge invariant. That's approach number one to quantizing a gauge theory. Approach number two, the one that is closer to the way I've been talking about quantization a lot in this course, which is to before I mention too, this approach does work and is good for high energy scattering processes, but it's not very good for dealing with processes at lower energies, like talking about ground state correlations and so on. This approach suffers badly there from the first problem, that the classical limit in the low energy case is very, very nonlinear, and it's very hard to evaluate these path integrals around that limit. Not impossible, just very hard. The second approach, which is much closer to the way I've been emphasizing you should think of quantum field theory, you think of it as a theory with a cutoff, and then you do all your computations in this finite cutoff theory, and then you run coupling constants to match experiments. This one here, putting it onto the lattice, is something that we're going to talk about because it has very many good features. One of them is that one becomes easy. Putting it onto the lattice allows us to deal with the nonlinearities of this theory. But we at least, in any version of the cutoff theory, lose Poincare invariance. So that's not the case when you do path integral quantization and you put a cutoff on, clever cutoffs. You can find cutoffs that don't break Poincare invariance. And so you can be at least sort of satisfied that this theory will have the Poincare group as its symmetry group. However, when you put something onto the lattice, there's no way you can leave Poincare invariance unbroken. As soon as you put a lattice in space-time, then you know you're in trouble with Poincare invariance, because with respect to a boosted frame, the lattice spacing is just smaller. So this is not going to work. At least naively, we're not going to be able to have our cake and to eat it. We're not going to be able to deal with the nonlinear part of this classical theory, the symmetries, and keep the symmetries. Now, this is kind of an ironic situation to find ourselves in. One way we can deal with analytically and describes high energy processes. The other, which is very good for computers, you put this into a computer and you can actually get like estimates out for experimentally accessible quantities. And at the moment, these things haven't been proven to be equivalent at like any mathematical level. So the status of mathematical rigor of this approach is, well, it's not particularly rigorous at the moment. There's still like work to do here. Although there's been kind of recent advances that makes us think that this is going to work out. On the lattice, things are perfectly rigorous because in the end you have a finite dimensional quantum system. I'll tell you about how to do that in the next lecture or the lecture afterwards. And everything's perfectly rigorous. It's just that to get back Poincare invariance when you let the lattice spacing go to 0, you take the continuum limit, that's sort of really hard work and no one's made any progress on that either. So we're at you're sort of at the cliff face of research right now. You'll be able to understand these theories, the definitions of these theories, but basically any question you can ask about the rigorous status of these theories will be an open question. There will be no answer. And so all we have to do now is to find ways to get finite answers for predictions and match them with the experiment. And then we just have to hope that sometime down the line, some clever cookie will work out how to make this stuff rigorous. Okay, so today I'm going to talk about the path integral quantization recipe, number 1. How do you do it for non-abelian gauge theories? I'll just go straight to non-abelian gauge theories. I won't even worry about U1. As soon as you see it for SU2, you'll know how to do it for U1. All right, what's the problem with path integrals? Maybe they just work. When they just work, they work really well. So we could just hope they just work. There's a third approach, which I didn't talk about, which is canonical quantization. That also kind of works. But in this course, we'll just discuss these two approaches. All right, here's the problem. Problem 2. So we have this gauge configuration and another one. Which is a gauge transformation away. Well, the problem with that, here it is. Now, I'll do it like this, put sigma A there over 2. All right. So simple statement about gauge invariance in these theories. Gauge invariance is a symmetry transformation, right? And it says that the theory is invariant under this transformation of this configuration A. So this came from last week, last lecture, and it is the result of doing a local symmetry transformation on this gauge helper field A mu A? There's a question?
Yes, what is the first letter supposed to be? This A, also an A? No, in the second equation, right
Here.
after the equal sign.
Here? Yeah, so this is A prime.
Sorry.
And then, yeah, the question was, is that an A as well? That's an A prime. So these two gauge configurations are different, right? You know, these list of 12 numbers here is a different list of 12 numbers here at every spacetime location. But the theory is invariant under exactly that transformation there. So the classical theory right up there, the Lagrange density is completely invariant under that. And now we start to see where things might go wrong with the path integral. Because if you integrate over all gauge configurations A, you just naively just say, this is how we path integral quantize, it's always worked before, it's going to keep working. Then you can see that there's an infinite number of different A configurations. They're different at the level of just being lists of 12 numbers, but the theory, the action, is invariant under this. So there's these equivalence classes of these A's. And when you sum them all up, they're going to give the same number, aren't they? So every configuration A, which is different from one particular chosen one by a gauge transformation, is going to evaluate to exactly the same number here, exactly the same e to the is. And then you have this sort of immediate infinity. Right? If you sum the same thing an infinite number of times, then that's going to spell sort of disaster, right? It might be that you get some crazy cancellation. Yeah, but, well, you know, praying doesn't usually answer your problems. You have to sort of get out and do some hard work. So I'm going to draw a picture of what's going on. And that is, we've got equivalence classes of these independent degrees of freedom here. So I want to draw a picture of what these equivalence classes look like. So this is a schematic picture of the space of all A mu's. So to draw this picture, you've got to imagine that at every point in space-time, there's a little copy of SU2. Well, at every point in space-time, there's a list of 12 numbers, is another way of saying it. And also, there's this little copy of SU2 at every point in space-time. I find that impossible to draw. So we're going to imagine a 0 plus 1 dimensional space-time. This is the only picture where I can sort of reasonably confidently draw what the space of all A mu's looks like. So 0 plus 1 dimensional space-time. What's a 0 plus 1 dimensional space-time look like? Well, it's just a line. And at every point in our 0 plus 1 dimensional space-time, we have one of these gauge fields A mu, except now mu, right, was a 4 vector in 4-dimensional space-time, but in 1-dimensional space-time, it's just a number. So at every point in space-time, you can think of the gauge field as just being a number, right? That's like this. And SU2 is acting on this gauge field, right? So there's, at every point in space-time, this SU2 can act essentially independently by multiplying by a phase. So I'm trying to draw this action as like a little copy of the circle. So there's a copy of the circle at every location in space-time. Well, actually, it's more for SU2, it's the sphere. and it's acting independently on this gauge configuration at every location in space-time. And so it can sort of twist around the field as it wants, multiplies it by a phase. And so, yeah, because this thing is a list of 3 numbers. So even in 0 plus 1 dimensional space-time, it's hard to think of the set of all of these A mu A's, because it's still a list of 3 numbers at every location in space-time. So here's the gauge group. So every one of these guys is like a vector on the sphere. The gauge group acts independently at each location in space-time. And you should think of one of these guys as really like a choice of a point on the sphere at every location in space-time. And there's equivalence classes of these configurations. So this local gauge group acts on one of these configurations and gives you an equivalence class of these A's like this. And the problem in the path integral, in applying the naive path integral, is that we're summing over elements of these equivalence classes. When really we should just choose one configuration from each equivalence class and just sum over that. Just for each equivalence class we choose one particular A configuration, and then for the next one we choose one particular one. Yep.
Why do we get the sphere for SU2 symmetry and not circle?
So for SU2, the group SU, why do we get the sphere for SU2 symmetry and not the circle is the question. For SU2, you can parameterize every element of SU2 with 3 numbers. There's a way to do that with quaternions. And these 3 numbers have to have length 1. So it's like a point on this 3-dimensional sphere. So 4 numbers. Now it works. Yeah, so every element of SU2 can be parameterized by 4 numbers, being the coefficients of the 4 quaternions, and then this list of 4 numbers has to have norm 1, which puts it on the 3-dimensional sphere, not the 2-dimensional sphere. That's why I've written S3 there. So even here, I find it a bit difficult to sort of, in the super trivial case, to illustrate to you what the space of configurations look like and how does the gauge group action look like. So there's a kind of more common picture that people use. So imagine we go to 0-dimensional theory now, invariant under the gauge group SO2. So their configurations are just points in, say, two-dimensional single particle quantum mechanics now, pre-zero dimensional, 0 plus 1. And we're looking at a theory invariant under some symmetry, right? So your configurations fall into equivalence classes. So if the theory is invariant under rotations, then the origin is invariant under rotations. It's a single point, it's a configuration invariant under the symmetry. But a point out here, well, under the action of SO2, it sort of rotates like this. And if your theory is invariant under SO2, then any point on this circle is equivalent. And furthermore, the further you go out, well, your theory is invariant under SO2, so any point on this circle here is equivalent, has the same action. And if you start to path integral quantize some hypothetical theory with this rotation group here, then you will have sort of reasonably mild but infinities when you just sum over all the configurations lying on this circle here, because there's an infinite some number of such points, and you will sum over them inadvertently when you do the naive path integral. You sum over all configurations, but there's this codimension one circle where they're all equivalent, and you get this sort of infinity there. So the one answer is to choose a representative per equivalence class. So these are the equivalence classes. And you just So I draw equivalence classes with square brackets around a configuration. And you choose a representative per class. And I've already essentially done that in this picture here. So if you choose the point on the x-axis where the equivalence class intersects it, that's a perfectly good representative choice. But you could have done it like this, right? You could have, every time a equivalence class crosses this particular curvy line here, you use that as your representative. These are different choices of representatives. Right? And we call these gauge choices. Fixing the gauge. So choosing one representative per equivalence class is called a gauge fixing condition. And then you happily integrate over the space of representatives. That's one approach to dealing with this symmetry. You first spend the symmetry to reduce your configuration space from large to small, and the smaller configuration space consists of all those configurations lying one per equivalence class. There's another approach which we exploit more on the lattice side than the path integral side, where you come up with a number per equivalence class. You never actually choose a representative. You rather assign a number to each equivalence class and then sum over the equivalence classes. Ultimately, that's what we do when we quantize things on the lattice. But for today, we're going to come up with a gauge fixing condition. And this will just be some equation, not curly G, but now it's going to look like this. Our gauge fixing conditions will look like A has to satisfy some equation. And there's multiple examples of such things which work to with differing amounts of success. That's one that we'll be focusing on a lot in this course, gauge fixing conditions that look like this. We've got a minus here. And you're familiar with these fixing conditions from electrodynamics. So when you express Maxwell's equations as a local gauge theory, you have this redundancy, right? Two different gauge configurations can lead to the same physical data. And you want to choose a condition to stop that redundancy, and you could choose things like the Lorentz gauge, which this is more or less like, or the Coulomb gauge, and so on. So there's various conditions that you're already familiar with at the Maxwell equation level. This is a generalization of these gauge fixing conditions to this non-abelian case that we're considering here. All right, so gauge fixing condition is expressed as an equation that the connection or this gauge field has to satisfy. And when you do that, picks out a unique representative per equivalence class. Or does it? A gauge fixing condition, if it's a good one, should pick out exactly one representative of each equivalence class. But some don't. It turns out that you can inadvertently make a gauge choice where this line curves back. And so then sometimes you pick out, say, 3 representatives for an equivalence class, or 0 if you're really unlucky. So it can go wrong. And this, when it goes wrong, this is called the Gribov ambiguity. And there's one gauge fixing choice which does have a Gribov ambiguity, and that's the Coulomb gauge. So we'll tend to avoid that one. So it's known that the Coulomb gauge can sometimes have more than one, it picks out more than one representative out of these equivalence classes. Yeah, question?
Why would you call this a gauge fixing?
So the question is, why would you call it a gauge fixing if it doesn't even work? Well, I guess, you know, in the case of U1, it does work. And, you know, by analogy, you think it might work, and you call it a gauge fixing condition. You don't realize it has a Gribov ambiguity, because it's very hard to study these things. And then someday, you stare really hard at the gauge fixing condition that you worked out, and you realize that all of a sudden it doesn't actually work. It's picking out 2 representatives. So yeah, it's precisely speaking, you shouldn't call it a gauge fixing condition if it has a Gribov ambiguity, but you can't tell at the beginning. That's the problem. Okay. So suppose we find some magical equation which does pick out exactly one representative per equivalence class. As I believe this is still current research to find like good such equations. Then Turns out, if you can find an equation satisfy that picks out just one representative per equivalence class of configurations, then you can separate out the overcounting in the path integral. You can separate the integral, the path integral up there, into two pieces: the integral over exactly each representative and the integral that goes over the equivalence class. And then, once you know that you got the integral over the equivalence class, you can just pull that out and throw it away. And that's what we're going to do.
Sorry, but I don't understand really why we are allowed to put this integral over the equivalence class away.
So the question is, why are we allowed to put the equivalence class integral away? Well, we'll see. It's not trivial. Like, I don't expect that to be obvious straight away why that'll separate out nicely. But if you look at this picture here, I'll at least give you an analogy, okay?
No, I see
Yeah.
that it would work, but I don't see why we are allowed to take away a whole integral.
So why are we allowed to take away a whole integral? Well, we're in the business of guessing a quantum theory here, right? And so we do whatever it takes to get that quantum theory. Now, if you have some dodgy, weird steps along the way that may or may not be entirely justified, that doesn't matter if at the end you get a healthy quantum theory that's invariant under these symmetries. It's like saying, you know, the end justifies the means, right? Yeah.
Another question, is it even known to be possible to find such gauge fixing?
Yeah, it isn't, but no, the question is it known to be possible whether you can find such gauge fixing conditions? There are some good ones, yes, that are known. My favorite is the temporal gauge, which we'll use when we work on the lattice. That's known to be a good one. And these ones here are also known to be good ones. But the Coulomb gauge, watch out, that one's. And it's not even clear if the Coulomb gauge is that bad, because as I just said, right, if you can write down a healthy quantum theory with the right symmetries, then you're done. The end justifies the means here. The path integral is just a helper. It helps you guess things. So now I gotta show you how to do that. Right? How do you separate out the overcounting in the path integral? How do you get rid of this naive divergence? Well, you do something clever, right? And as sort of somehow a large majority of arguments seem to boil down to doing this, right? You insert the number one, but you insert the number one represented in an extraordinarily clever way. So the number one can be represented in so many interesting ways. And here's one of them. Okay, this is a bit bamboozling as an expression. Why on earth is that equal to 1? Well, firstly, I should at least define the bits and pieces inside. And I should tell you, what is this A alpha? Well, A alpha is the connection, the gauge field transformed by local gauge transformation. So it's none other than the guy we just saw before. I'll write it out without the help of the sigma matrices. Okay, that's the oh, these are the structure constants. For the Pauli sigma matrices, I guess there must be an I here. Yeah, so this is a bamboozling way to express the number 1. But we'll see how useful this is in a second. But first I've got to argue to you that it is in fact the number 1. It's all very well to say that 1 on the left-hand side equals this thing. I have to prove to you now, or at least argue, that this is in fact a true expression, that indeed this is the number 1. So this is the functional derivative here. That delta is the functional derivative. So I think everything basically makes sense. Oh, and then I've got functional Kronecker delta. I see that there is some potential for confusion here. Functional Dirac delta, let's call it. That delta there. Okay, so this is this expression here makes a lot more sense if you define the path integral as the limit of just many, many integrals. So there's a way to represent the number 1, which you're probably a bit more familiar with. And that is, you represent the number 1 as the integral of the Dirac delta function. Okay, so that's like, I hope that's a bit more familiar, right? The Dirac delta function, you know that if you integrate over it, you get the number 1. And that's what we're doing here. So this is what I've done, right? You know, whenever you see a path integral, to get some feeling for what on earth's going on, you should always discretize it and break it into just many, many normal integrals. That's what we're doing in this first step here. And then replace all these words with their many variable counterparts. So this functional Dirac delta is an infinite number of delta functions. But when you discretize this integral here into just n integrals, that just becomes the n-fold Dirac delta function. This is a much more well-behaved object. This constraint G A alpha equals 0, well, A of alpha is now just a list of numbers A. It's a vector of n numbers. And that condition dNGA is, well, there's just some function of this vector A. And then you've got this delta, this Dirac, this determinant over there. But if you look at that for like a little bit, then you see that this is just under a change of variables. This is an exercise. This is just the n-fold. This is something that you really know. It's just that. It's just the integral of the Dirac delta function. And that's something that, you know, I hope you're willing to accept that that's the number one. And if we do a change of variables, we can end up with that expression, which is then the number one. And then this is the discretized version of this thing over here. So if we define this identity now as just the n is infinity limit of this identity, then I hope this crazy looking expression starts to make some sense. Well, well, well. And that determinant, by the way, is the Jacobian of the change of variables. Yeah. So we're going to now insert this number 1 into the path integral. Let's see what happens. So we get all right, now we've got two problems. We started off with 1, now we have 2. We started off with having to deal with the path integral, which had these obvious overcounting. We've inserted the number 1, which has not clearly done anything at all. And we've furthermore given ourselves a horrible mess to deal with, namely this determinant here, this coming from the Jacobian of that change of variables there. This is called the Fadeev-Popov determinant. So this thing here, this is a very promising object altogether. What does this do? This says per representative of the equivalence class, this is 0 unless A happens to obey the gauge fixing condition. So then if you look over here, you see that you integrate over all A's and then over all gauge transformations. So this integrates over the equivalence classes, and you can suck out the overcounting here into this integral here. It's just by a change of variables. And then you've separated this integral now into integral over representatives times by integral over gauge transformations, and then this object here selects out one representative per equivalence class, and then you'll have an infinity just from this part here, and then hopefully that decouples and you can throw it away. That's the strategy. The price we pay, however, is we have this Jacobian that we have to evaluate, this Fadeev-Popov determinant. And it's sort of super far from clear how you might do that. And this is where the full genius of the approach comes. It's in dealing with this determinant here. And like, at this point, like, you know, determinants are nasty nonlinear things. You would think like this is hopeless. But I invite you to remember something about fermions. And this is an interesting thing. So firstly, what is dGA alpha d alpha equal to? Well, if we choose that particular gauge fixing there, which I promised you was a good one, then you can work out this transformation here. It's a very good exercise. I will not prevent you, I will not deny you the joy of doing this. I'll make you very happy to do this exercise. It's sort of not ridiculous to see how this might come. Let's see if I have still on the board. Yeah, take a look at this. That's the result of doing a gauge local gauge transformation of A. What happens is you take your connection, your gauge field, and you replace it with A plus the covariant derivative of this thing there. And then if you stick this thing into here, well, you have to evaluate the result of doing this on that. So you get these d mu's and a's, and then you have to do the functional derivative with respect to alpha. Now remember, I sort of defined functional derivatives by example a bunch of lectures ago, but you do that example and you see that things start to pop out quite nicely. So we have this expression now for this Jacobian, the determinant of the partial derivative of the covariant derivative. Now this is an operator, so that's at least good, right? At least we sort of somehow got something that looks like a matrix. Because when you take a determinant, right, what you put in there better be a matrix. Otherwise, something's gone really wrong. So we've got here an operator. An operator is just an infinite dimensional matrix. There's really no harm in thinking of it that way. And we're taking the determinant of this infinite dimensional matrix here. So that's not particularly genius, that's just substitution. But here comes the genius step. Am I going to do it now? Yeah, let's do it now. Yeah. This is just so fiendishly clever. This is so weaselly and cunning. I really love this. So when we did path integrals over fermions, we noticed a little formula I asked you to remember. And that is that the determinant, that the path integral over Grassmann numbers gives the determinant. You know, when you have a Gaussian Grassmann expression, You do the Grassmann integrals, you get this determinant instead of 1 on the determinant. But look at that, that's a determinant. So we're going to exploit that trick, exploit that observation to come up with this extraordinary trick here. So this is Grassmann. So those C's, what are they? They're Grassmann valued fields. Yeah, a question? Is the G missing? No. Oh, yeah, the one on G. Yeah, that's definitely missing. Yeah, there you go. So this is just a mathematical step, right? You take this observation that the determinant of a matrix can be expressed as a path integral over some Grassmann valued functions, this matrix here, like that. And this is extraordinarily interesting for doing our path integrals, because this here is a local expression in these C's here. Remember, C's are Grassmann valued fields. Now there are some things to notice about these C's. They're a bit wrong. They're not spinor fields, they're scalar. They have the wrong spin, spin 0. So they probably don't correspond to anything physical, which is why they're called ghosts. And as we proceed, these ghosts will appear everywhere through our expressions. And in order for things to be all right at the end, we need that any expression for any observation cannot depend on these ghosts. They must disappear for all predictions. They must cancel out. And so it turns out that they have just the right properties to do precisely that when you do your calculations, they will cancel out. And what they do is these cancellations, they introduce minus signs which delete the overcounting that comes from just the naive path integral here. So after this extraordinarily clever step here, we've managed to reduce this nasty, incredibly evil-looking path integral here to one that's much more tame. It's going to be an integral over a, psi bar, c bar, of some exponential of some action, some local action, with a delta function here. And that delta function picks out one representative per class, and we will actually have a local expression. So let's get to that. We're not quite there yet. Right, so after all these steps, we've ended up with this thing here. It's still exactly equal to our original path integral. Now we've got this omega A hanging around, and it's arbitrary. So we can do what we like with it. It's like this extra degree of freedom we've added in. And we've also got this annoying delta function here. So we're going to get rid of that annoying delta function just by using just by integrating out over this omega A. That'll use up that delta function here. And so the way you can get rid of that omega A, which is a function, is you just do a Gaussian integral over it, and that should equal 1. Right, so this, all these other path integrals here. So I'm just going to stick this together and call this S prime. So this expression here depends, it does not depend on omega A. Sorry, this expression depends on omega A. This is the gauge fixing. But it's arbitrary, and so you can integrate that out there if you want.
Sorry?
Yeah.
Did you miss the integral over capital A?
The question is, did I miss the integral over capital A? I certainly did. And that's all in here. So this omega A is an arbitrary gauge fixing. So that takes a representative from each equivalence class. So if you choose a different omega A, you get different representatives per equivalence classes. But the overall physical answer cannot depend on that choice. So as long as you integrate, so the answer to all of this path integral here will be the same irrespective of omega A. So you choose, say, omega A is 0, you'll get an answer. You choose omega A is 1 everywhere, you'll get an answer. But those two answers will be the same for all physically observable quantities because this is a gauge choice. It's just a choice of representative per equivalence class. You're just changing which representative you're summing over. So actually it is independent of omega A, the result of this full path integral. So why don't you integrate over 1? That's what we're doing here. This is a standard Gaussian path integral here. It will evaluate to 1 if the argument doesn't depend on omega, which it doesn't. And we can push that integral past the others because, you know, at this stage you can exchange integrals whenever you want. So let's go ahead and evaluate this path integral over omega. While I'm erasing the board, you can look at this and start to imagine what the answer is going to be. You do the path integral over omega first, and the delta function forces omega to be equal to delta mu a mu. And so in that exponent there, that quadratic exponent, you get rid of the omega a and you replace it with delta mu a mu squared. And that's exactly what happens. And the path integral becomes, well, there's some constant that will depend on that psi. Psi is some number. I haven't set it yet. I think we'll set it between 0 and 1. So you get some number that depends on the constant. Then you have all these path integrals that you have to do. A d psi bar, d, what's the one that's missing? C bar. And then you have e to the power of I d for x some new Lagrange density L prime prime. And I'll write out now this Lagrange density. So you've got the original stuff. And then you've got this term that comes from that integral over the omega. That's what came from the integral over the omega. Then we've got the ghosts. Which in components look like this. And then we've written down a very interesting looking expression. Now, this delta alpha, this integral over the alpha here, well, everything from the right of this point doesn't depend on alpha anymore. If you look at this thing here, there's nothing that depends on alpha. We've eliminated the dependence on alpha. So this indeed evaluates to infinity now, this path integral here. We can evaluate it straight away, right? So the result of doing all these transformations is infinity. That's coming from the integral over d alpha. But of course, we're going to divide out by this infinity in all of our expressions for correlation functions. So So in expressions for correlation functions for our theory, we always have ratios of path integrals. So we always end up with some path integral over some stuff, correlators, divided by the path integral without the fields being inserted there. And in those expressions, these infinities and these n xi's just cancel. And you're left with just integrals over the configurations which are gauge, one representation per gauge equivalence class. So let's look at this object here for a little bit. This is a very interesting object indeed. What have we got here? Well, we've got what looks like a pretty standard path integral over some pretty standard fields here. A are now just bosons, and these psi's are just fermions. And we've got these C's here. What are these? Well, these are these ghost fields. 3-component things. each a scalar, each transforming as a scalar. And you look at this and you go, oh, this is just a normal looking path integral. All right, we have some quadratic stuff. This is all nice and quadratic. There's some non-quadratic stuff inside this covariant derivative here and some non-quadratic stuff in here. And then the first thing you might try is, like, let's assume that this g, which I told you was big, this one on g, which I told you was big, no, g is big. Let's make g small and use perturbation theory and see what we get when we evaluate this path integral here. So that's a legitimate way to approach this object here. And then do we see what kind of quantum predictions do we get? So the big question is, let's call this star star. Right? Does star star define a quantum theory at all? When you start working out correlation functions, you might find that they don't obey positivity, for example. If they don't obey positivity, then you don't even have a quantum theory. The problem with the path integrals is there's never any guarantee that what you get out is a quantum theory, that its predictions come from some Hilbert space with some Hamiltonian. So that's a big question. Does it even define a quantum theory? And if so, is it invariant under the Poincare group and local gauge transformations? Unclear, right? It's very unclear. And one mostly related but not quite related question is, do these ghosts, these auxiliary fields C that we had to introduce to evaluate their determinant, do they actually vanish from predictions? Do we have processes where, let's say processes, I think is probably a better word, because they're always built into the predictions, of course. I mean, to get a prediction, you have to integrate over these C's. No, but we don't want that they appear. We don't want there to be a process. We don't want there to be a matrix element which takes a Dirac field to a ghost field, for example, because that would mean that this theory, whatever it is, if it is a quantum theory, would allow for a Dirac field to transform into this ghost particle. And this ghost particle is nothing we've ever seen in an accelerator. So it better be that whatever process you write down, if it starts with 0 ghosts, it must end with 0 ghosts. And that there are no matrix elements, no probability amplitudes to go from no ghosts to some ghosts. That would be extraordinarily bad. So these are the big questions that we need to address. And to a large extent, I'm going to not address them or argue that they can be addressed, or give you some hints how you might address them, and largely not deal with them in this course, because it's a big topic now, a big task to actually address question 1 and 2. And of course there is a question 3. Presumably this theory is going to have actual real divergences, which means that the predictions will depend on you have to put a cutoff on, and the predictions are going to depend on the cutoff, and you have to take the cutoff away and adjust coupling constants. to make the predictions independent of the cutoff. That's presumably the case, and it really is the case for this theory here with this particular Lagrangian, that it does have like real divergences. And then you have to ask the question, is it renormalizable? Is it possible to add counter terms that can balance the effect of the cutoff on predictions at low energies? Now that's a big question, but that's one that's been resolved, right? So this is the work of a Toft resolved this big, serious amount of calculations that has shown that this particular theory is indeed renormalizable. There's no hope that we'll cover that in this course. Lots of hard combinatorics. I'll certainly give you a hint as to how 2 will happen. In fact, we'll more or less see it when we write down the Feynman diagrams for this theory in the next lecture. And as for 1, yeah, there's not much I can say about that. But we are convinced now, particularly by the work of Toft, that 1 is in fact true as well. There is some quantum theory that's buried in this prescription here. But for now, I think I'll stop here. Thank you very much.